Thank you. Thank you very much for the introduction. So good morning, everyone. Thank you for attending this talk. The talk is going to be mostly a kind of educational talk. We're going to talk about scaling Ethereum. And I don't know if this is working. Yeah. OK. So this is more or less the outline of the talk. First of all, I'm going to give a little bit of the background on scaling Ethereum, how we started doing this research. This is going to lead to the changes we have done on the recent years, so the DNAP hard fork, the Pectra hard fork that just passed about a month ago. And then I'm going to talk a little bit of what are the plans for the coming hard fork, which is Fusaka. Especially, I will talk about PRDAS. And then I'm going to talk about what is the proposal that we want to do for the changes we want to see in the peer-to-peer network for scaling beyond what we have today. And then we are going to end with some conclusions. So as I said, the background of this talk is at some point we wanted to scale. At the end of 2017, we realized that the number of transactions per second that Ethereum makes is not enough to, englobe the whole digital economy on the blockchain. So we wanted to change this. We wanted to go much higher in terms of transactions per second. And so the mission that we set up at that time was we want to scale Ethereum several orders of magnitude beyond what we have today. But we want to make sure that when we do that, we keep the system decentralized and secure, okay? And this is kind of a trilemma, because it's very easy to scale if you give up on decentralization, but if you want to keep decentralization, then the problem becomes much harder. And when I mean decentralization means that anyone can run a Ethereum node with a relatively cheap hardware and a low network bandwidth, and achieving this is quite complex. So first, in 2018, there was this sharding roadmap in which we were supposed to have multiple shards that will communicate with a main chain and so on and so forth. This idea was changed later on 2020 to a rollup-centric roadmap in which the scaling solution will be based on rollups, right? And so since then, since 2020, we started focusing on rollups for scaling. And this is going to be the way we are going to be able to achieve many transactions per second and much more bandwidth and throughput in the whole Ethereum ecosystem. But the problem is the rollups need a space. Rollups need some space to put their data, okay? So this leads to the changes we have done in the recent years that I'm going to explain here. So first, if you are familiar with the EVM or with the Ethereum virtual machine, there is a thing called data, where you can actually store data in the blockchain. Now, this is nice, but it has three main problems. The first problem is that the data that you store there is going to be there forever. Okay? Whatever you write with cold data is going to be stored on the Ethereum blockchain forever. So that's one concern, because actually for rollups, we don't need to store this data forever. It's just a temporary storage. The other problem is that you have limited space, only a few megabytes of storage per block in cold data. So that's not enough to cover all the rollups that we want to use in order to scale. And the other problem is that it's kind of expensive storage. So you have to pay something like 16 gas per byte with cold data. And so that's also kind of expensive. And the reason it's expensive is because you are storing this data there forever. So that's a problem. So to solve this, we came up with an idea. We invented Tinder. I mean, blobs. But you can think of blobs like the Tinder of Ethereum, okay? So if you don't want this long-term commitment that you take this forever, if you don't want that, if you just want a snack, I mean a snark, if you want to store a snark for your CK rollup for just a temporary time, then you can use blobs. And with this, you can really solve all these three issues. The first one is that the data that you store in blobs is not there forever. It's only going to be there for 18 days. So that's fine. That's enough time for the rollups to guarantee security. And that's all what we want. Now, the other thing is that you have more space. You have tens of megabytes, even hundreds of megabytes, if we manage to do what we want to do, which is what I'm going to present today. And it's also cheaper because it's an independent market, right? The gas, the data that you put on the blobs is an independent market than what you put on chain, on the layer 1, okay? So because of this different structure, we managed to solve these 3 problems using blobs, and that's the difference between cold data and blobs. So that's all great. And so in the previous hard fork, which was called Deneb, it was launched in March 13, 2024. So we have been running this for about a year, and it has been running quite well. The figures that you see here on your left is how many blobs per block have been used. This picture was taken around the time of DEF CON in Thailand last year, so about 6 months ago. The blue color is 0, so that means about 40% of the blocks have no blobs. That means we are not using the maximum capacity of the space that we could have using all the blobs. The pink part is the ones that are storing 6 blobs per block, which is the maximum that we have on Ethereum, or that we had with the Deneb hard fork. And so that shows a distribution of how the blob market is being used, or it was being used about 6 months ago. And on the right side, you see more or less the latency of the propagation of blobs over the peer-to-peer network. This is important because in Ethereum, you have to produce a block every 12 seconds, which means that you have to transmit the blobs within the first 4 seconds of the slot. If you don't manage to do that, maybe the block is not going to be taken into account because you cannot guarantee that the data is available. And what you see here is that the blobs from 1 to 6 are being transmitted actually within the first 2 seconds of the slot. Okay, so that's more or less the time that it takes to propagate all the blobs in the peer-to-peer network that we have in Ethereum. So that's great. That works very well. And about a month ago, we did another hard fork, which was Spectra, or Electra Prague. And what I show in this picture is how the blob market has changed before Spectra and after Spectra. So this figure shows 10 days before the hard fork and 10 days after. In blue is before, and in yellow is after. And on the x-axis, you see how many blobs we are using. So before Spectra, the maximum was 6. So that's what you see, 6 is the peak on the blue curve. And there is nothing after, because that was the maximum. In Spectra, we changed the maximum up to 9 blobs, and the target is 6. So now we see that the yellow curve is pushing a little bit toward the right side, because now you can publish more blobs per block. So that's great. Now we have more blobs. This makes, so if each blob has about 128 kilobytes in size. So if you send about 9 blobs in a block, that means that you have to download something around 1 megabyte in 12 seconds, which is relatively easy with the internet connections that we have today. So that's all okay. Now I want to talk about what is coming tomorrow. So the next fork is Full Osaka, or Fusaka. And what we want to introduce there is something that we call PRDAS. So PRDAS the idea is basically we have to cut the blob data and make the nodes in the system to store only part of the blobs and not the whole content, okay? For 2 reasons. First of all, we don't want to store all the blobs because that's too much storage, but also we want to reduce the network bandwidth that we use for acquiring the blobs. Now, what is the problem of that is that if you only download part of the blobs, you are not really sure that the entirety of the blob is available, and that creates a problem that we call data availability sampling, and that's what we are trying to do. So we want to make sure that the blobs are available even when you only download one part of the blob. So this is how it works. First, the blobs are disseminated over the peer-to-peer network in the execution layer. The execution layer nodes download the blobs by pooling. The consensus layer nodes extend the rows with erasure coding using Reed-Solomon encoding. And then the data is divided into 128 columns, okay? And then every node in the network has to download a minimum 4 of those columns. If you want, if you run a big node because you have many validators or because you have a block explorer or whatever, you can actually decide to download all the columns, and basically you will have the entirety of the blobs in your node. That is up to the node operator to decide whether they want to download 4 or 8 or all the columns. Okay? But the minimum is 4. So this is what we have today, and then we do sampling through column sampling. So we have to sample the columns. The entirety of the column is disseminated over the gossip sub layer. So this is what we plan for tomorrow. Now, at this, we have been working on this for at least 1 year, if not more. And this is more or less already set up. We have already testnets, devnets that are running PRDAS with multiple nodes. And so this is more or less kind of already settled. Of course, there is still a bit of work to do, but this is working already. Now, what I want to present today, the new thing that I want to present today, are some ideas that we can implement in the peer-to-peer layer to improve over what we have for PRDAS. So what we want to do is to scale up to 256 blobs in the near future. That's about 32 megabytes of data every single block. And this, you have to extend it with a ratio coding. So the real data is only the blue part of this square. You are going to extend it with Resolomon encoding horizontally, and then you extend it vertically so that you are multiplying the size of the data by 4. So instead of 32 megabytes, that makes 128 megabytes. So that's a lot of data that you have to disseminate over the network. Okay? So what we want to make is a system in which the execution layer nodes do not need to have all the blobs in the blob mempool. And the consensus layer nodes do not have to custody all the blob data as well. So there is sharding, data sharding, that happens both in the execution layer mempool and the consensus layer custody. And we wanted this to be easy on the network bandwidth for home stakers. So we propose 2 changes. The first one is blob mempool sharding system, in which the node decide which blobs to download according to the hash. So every blob has a hash, and you take your own node ID, you hash it, and then if the last character or the last half byte of your hash correspond to the hash of the last byte of the hash of the blob, then you download it. Okay? So by using this technique, what happens is that the nodes will only download 16 out of the 256 blobs that will come with every block. Okay? This accounts for about 2 megabytes of data to be downloaded every 12 seconds. So that's more or less double of what we have today in terms of bandwidth requirements, but we are multiplying the number of blobs by, from 10 to 250. Okay? So we're multiplying the space by 25, and we only pay 2 times in network bandwidth. Okay? In a network with 8,000 nodes, which is more or less what we have today, that means that every blob will be stored in about 500 nodes. Okay? So that's quite a strong resilience out there. So there's a lot of replication going on, even if we shard in this way. And we're going to start implementing this today. We don't even need to change the specification of Ethereum. We can actually already implement this and let nodes decide whether they want to download everything on the execution layer mempool, or if they already want to shard it and only download part of the blobs. So what you will have as a result is a network that looks more or less like this, in which different nodes, depending on their PRID and the hash of their PRID, they will have different blobs, and then between the whole network, all the blob data will be there, and it will be replicated enough time for the system to be robust, even if you consider that a large portion of the nodes could be malicious. So the second proposal that we have is what we call partial column dissemination, which is today what we have is you have to download all the blobs, and then you send the entire column over the gossip sub network. What we propose is to be able to send a partial column, not the entirety of the column, but only part of it. Why part of it? Because only you have part of the blobs. You only have some of the blobs, and then you can just send the parts of the column that you have. but maybe you don't have the whole column, but that's fine. You just send the parts that you have. And we can implement this today as well. I mean, it's not very complex to pass from sending an entire column to only send cells. That's very minimal change in the network implementation. And so what that looks like is like, OK, you have some blobs, only the ones that are corresponding to your hash, to the hash of your node ID. You extend those using Reed-Solomon encoding. And then you disseminate the columns that you have to disseminate on the gossip subnetwork, but only part of the columns, OK? But then if multiple nodes, if all the nodes do that, then creating the entire column with the, joining the pieces of multiple nodes is extremely easy. And then everyone in the network will end up with the entire column, even if no node in the network is sending the entire column. Okay? So that is extremely easy. And then once you get the column, then you can extend vertically using Reed-Solomon encoding, and then you go back to the two-dimensional structure that I presented before. And then you have different nodes that have different blobs, but they also have different column IDs, and they all disseminate on their corresponding gossip subnetwork, and everything works fine. We retrieve exactly the same structure that I showed initially. Okay? And what is good about this is that, again, we managed to have a structure that is two-dimensionally erasure-coded. The execution layer nodes do not need to have all the blobs in their mempool. The consensus layer nodes do not have to custody all the columns, but only parts of the column. And this is quite easy on the network bandwidth, even for home stakers, which was the purpose that we had from the beginning. So I was quite fast. Conclusions, if we compare the two systems, on the left you have more or less what we are proposing right now for PRDAS, and on the right is PRDAS plus the two changes that I just presented right now. So on the one side you have the execution layer nodes have to download all the blobs. This is what happens today. Okay? On the other side, by introducing the sharding in the mempool, the execution layer nodes only download part of the blobs. Okay, so you are reducing network bandwidth stress there. Now, the other thing is that in the mechanism that we had planned for PRDAS, you have a block, the block builder or the block proposer. We are going to assume is the same for simplicity. Has to disseminate everything to the network. So it has to create the blob, do the ratio coding horizontally, then vertically, and disseminate all the columns and rows to the entire system. That means that if you are a block proposer, you really need a really good network bandwidth to be able to upload all the data that you want every time you want to propose a block. Okay? And that is quite a high demand for home stakers, because that means you have to be able to upload 128 megabytes of data in the first 4 seconds and send this to the entire network. Otherwise, the other validators will not see the data in time and will consider your block as missed. So in the other proposal here, we only have to send, the block proposer only has to send the execution payload, and the dissemination of rows and columns happen in the entire peer-to-peer network. The block builder doesn't need to send the rows and columns because it's already happening through the partial dissemination columns that I just presented. On the previous proposal, CL nodes have to download rows and columns. In this proposal, the consensus layer nodes do not need to download the rows because they are going to get them from the execution layer. Okay? So you have a code that is called get blobs, and you just get the same blobs that your execution client got previously, and it's pretty much you have to custody the same rows, and so you don't need to download those over the network. So that is already good because you are already reducing a lot of bandwidth that is unnecessary. And the other thing is that the consensus layer only have to download some rows and disseminate the partial column. So also dissemination-wise, it's also efficient because you are not sending the entire column. You only send the little parts of the column that you have. Okay? Now, there are several options that are important to take into account. For example, we can consider that the block builder disseminates the whole rows and columns, but only on a best effort approach, meaning that it's not necessary for him to do this really, really fast, because the entire peer-to-peer layer is already taking care of the dissemination of data. So he only does this as a kind of plan B in case the dissemination on the peer-to-peer layer doesn't work as fast as we want. So it's not like it's critical. It's not in the critical path. It's just a plan B in case the peer-to-peer network is having issues. Okay? So that's one thing. Another thing that you could add to this strategy that I presented today is mempool tickets. Mempool tickets is an idea in which you only can introduce a blob in the mempool if you get a ticket. And this is to prevent denial of service attacks, or if you want, you can avoid somebody trying to flood your mempool with blobs that are never going to be introduced in the chain. So this is something that can be done. But honestly, with this system, since we are horizontally sharding and not vertically sharding, the mempool is not really necessary. You could use it, but it's not really, I think, necessary at this point. Now, another thing that we could add to this, to this strategy is the use of I don't want messages. Okay, so once you receive the blobs on the execution layer, you can disseminate I don't want messages to stop receiving the blobs that you already have, and this is a way to reduce bandwidth as well. Many of the implementations that we have today in the consensus layer already have I don't want messages implemented, so we can make use of those in order to reduce bandwidth over the network. Another good aspect of this is that since the dissemination of the blob data doesn't start from one single point, which was the block builder, but it starts from everywhere, the entire peer-to-peer network is disseminating blobs and then disseminating partial columns. This is really good for anonymity. And this is something that we have proposed in the past. We call this a push-pull phase transition. So let me just very quickly try to explain the idea. What we wanted is to reduce network bandwidth, because we noticed that when you disseminate something on the Ethereum network, after 5 hops, pretty much like 98% of the network already received the data, right? So what we wanted is to say, okay, once you have done 5 hops, maybe you can say, you can stop pushing and transition to a pool-based strategy in which you don't send the entire blob. You say, I have this blob with this hash. If you are interested, let me know, and I will send it to you, right? So it's a transition between pushing, which is, here is the entire blob, to, I have this, if you need it, send it, which is gossip, right? So this transition is nice. The problem of doing this is that every time the block proposer sends this data and sends this with, this is the hop number 0, then everybody knows that your node is the block proposer, is the block builder. And so that means that you could de-anonymize validators in the peer-to-peer network, which we don't want. And so that was an issue, and that's one of the reasons we were not really sure if we could implement, if we wanted to implement push-pull phase transition. But with this idea that I presented today, with partial dissemination, we avoid this problem, because now the data is not being disseminated by the block proposer, but is disseminated by everyone in the network. So even if you receive messages with hop equals 0, that means you are the first one to receive it, it doesn't matter, because that doesn't say that you are the block proposer or the block builder. That you say that you have some blobs that somebody sent to you, and that's fine. Okay? So that's one of the advantages of this strategy. And yeah, another thing that that is important to take into account is somebody asked me, okay, but if you are the block proposer, okay, and you only downloaded part of the blobs, how do you make a block? Now you have to propose a block. How do you make a block if you don't see all the blobs that are available in the mempool, right? Maybe the blobs that you have are not that, nice in terms of economics, right? Maybe you want to make sure that the block that you propose is going to have the best blobs, and you will take as much advantage, economically speaking, and get as many rewards as possible. And yeah, this is true. But then what you could do is, because in Ethereum, you know that you are going to propose a block in advance, like an epoch in advance, so that's 6 minutes at least in advance, you can change the way your mempool works temporarily. All right? So once you know that you have to propose a block in the next epoch, you can transition to a system in which you say, OK, temporarily, I'm going to download all the blobs, not only the ones that fit my node ID. I download everything just until I propose my block. So I have the list of all the blobs, and then I can build the block that I want. I send the block, I propose my block, and then after my proposal pass, I can just switch and say, OK, now I go back to the sharded mempool strategy that I had before. So I can temporarily change this in order to propose a block locally. Okay? So that's another thing that we can have with this strategy. And I think with that, that comes to the end of the presentation. If you want to see the work that we are doing, you can scan these QR codes. Thank you very much for your attention.
Thanks a lot, Dr. Leonardo, from my end as well. So any one of you got any questions? So feel free to ask. We have a few minutes.
I was too technical.
No one? OK, so maybe I will ask you a very generic question. So what's your roadmap for the next 5 years? What exactly are you planning to do?
Good. So the plan is, as I said, for the next fork, for full Osaka, we plan to have PRDAS implemented and running there. So that's already data sharding at the consensus layer. We are also talking about sharding the mempool in the next coming months. So what you could expect by 2026, you already have a system which is sharded in the execution layer and the consensus layer. This is for next year what we expect to have. And the idea will be to have around 64 blobs, if everything goes well, by Fulu. Okay, 64 is much more than today. We have 9. So 64 is already quite significant. And then the next step will be what we call full DAS, which is two-dimensionally erasure coding, and hopefully 128 or perhaps even 256 blobs, and that you could hopefully expect this to happen maybe in 2027 or something like that. By then, we would have enough space and throughput for all the rollups to put the data that are required for the ecosystem to scale to a much, much larger number of transactions per second and throughput. That's the plan.
Perfect. That sounds wonderful. I wish you a great success for your journey. Thank you.
Thank you.